Thank you so much for the invitation and for organizing this, and thanks to all of the folks at IPAM. So even without the free food buffet, this is still my favorite workshop series to go to. And I also just want to point out, I think the last talk really showed us one of the benefits of kind of this online format is really bringing back these wonderful chalkboard talks that we all grew up with. So that was really a pleasure to see. Okay, so today I'm going to be talking about machine learning for fluids, which is a subject I'm very passionate about, and we work a lot in my lab to try to understand these systems. And before I jump in, I want to acknowledge many of my great co-authors and collaborators on this work. A lot of this has been done with Nathan Kutz and Jean-Christophe Loiseau, along with many of our postdocs and graduate students who are pictured below. And this is a small fraction of kind of the super group that's been working on these problems with us. So I'm just going to show you a little vignette of our work today. And, you know, when I talk to executives, like I go to Boeing and I talk to them about machine learning and what it can do for them, I often get this feeling that they think, you know, machine learning is a magic wand. You have some engineering problem that's tricky and costs a lot of money, and you're going to point your magic wand at that problem, and poof, you know, it's going to get easier with machine learning. And so I really want to demystify a little bit and kind of put this into simple terms, what I mean by machine learning. And I would say, at the end of the day, machine learning is really a set of advanced optimization techniques that leverage the increasing wealth of data we have in physical systems, from experiments, from simulations. And so, you know, this modern era of merging machine learning with engineering tasks, I think, is really exciting, because most of our engineering tasks, in this case in blue, I have my fluid dynamics tasks, can be thought of as challenging optimization problems. So control theory is inherently formulated as an optimization problem. It's optimization constrained by the dynamics. Model reduction is an optimization. You're trying to find the best subspace and the best model given some order to represent your data. Sensor placement, actuator placement, you name it. We are constantly faced with challenging optimization problems in fluid mechanics. And they're challenging precisely because they're high dimensional. The data is high dimensional. Our discretizations are high dimensional, because they're multi-scale in space and time. So there's a high intrinsic dimension of the system, because the Navier-Stokes equations are nonlinear. And this all leads to these very high dimensional non-convex optimization problems. There's lots of local minima. These are hard to solve. And there's no one size fits all method to solve these problems. And that's exactly what machine learning is getting really good at. So if you think of, you know, image processing and movie captioning and things like that, those are multi-scale, non-convex, high-dimensional optimization problems. So a lot of technology transfers directly over to fluid dynamics and to engineering systems more broadly if we know how to think of pairing those problems. Okay. And I'll point out, you know, we're all here because we love fluid dynamics, but you name, you know, your complex system, disease modeling, neuroscience, climate, financial markets, these all have the same basic flavor: high dimensional, nonlinear, multi-scale in space and time. Okay. So this is very kind of universal ideas here. And I'll point out that the simplest thing we can do, and probably the most immediately fruitful, the lowest hanging fruit, is trying to find ways in which our data in fluid dynamics looks like an image sequence, an audio sequence, or a movie. Because we can take off-the-shelf tools in machine learning, billions of dollars of industry investment in understanding that type of data, and we can directly apply it to our problems in fluids. Okay, so that's what I'm going to talk about in the first part of the talk. And then I'm going to transition into how we're using this for nonlinear model reduction to get really good low order models of very complex fluids. Okay. I'll point out a lot of this is covered in this recent review paper I wrote with Bernd Nowak and Petros Koumatsakis in annual reviews. And so this gives some of the literature. So if you want to kind of dig deeper into some of these things and find out where the seminal papers were, hopefully this would be helpful. So the basic idea in lots of data-driven fluid mechanics and in machine learning is fundamentally boils down to the fact that patterns exist in your data. So there are dominant patterns, even in these very high-dimensional complex systems. There are a few key patterns that matter for, if I'm an eagle flying, there's a few key flow structures on my wing that matter for lift and drag and turning for my daily life. And similarly, when I look at these high dimensional flow fields, often patterns emerge. And this is the same principle that allows us to do machine learning. And it's going to be what allows us to apply those techniques directly to fluid systems. I'll point out a lot of early data-driven image sciences, like for facial recognition, actually came from the fluids community. So Eigenfaces was published by Sirovich, 1987. In the same year, he applied the same algorithm to do a decomposition of fluids using the SVD. Okay, so this, very intrinsically related two fields. Okay, so I want to walk you through one example of how we can use image sciences, if we treat our data like images and respect the fact that patterns exist, to do a lot with relatively little. Okay, so this is great work by Isabel Scherl, who's a PhD student with me and Brian Palagi at University of Washington. And what we have here is a movie of a simple flow past a cylinder at low Reynolds number with a tremendous amount of salt and pepper noise. So occlusions and lots of outliers. We literally just randomly take 20% of the pixels at every time step, and we make them plus or minus 10. Okay, so we just black them out, essentially. And this is a really, really hard problem. What we want to do is clean this flow field. And so what we want to do is decompose this movie into a low rank movie, which is clean, plus a movie that contains only the salt and pepper noise, the sparse outliers. Okay, and this might seem too good to be true. This might seem like magic. There are infinitely many ways I can take my movie and split it into the sum of two movies, right? This is not unique at all. So again, if I think of this as an optimization problem, how do I write the optimization problem so that I promote a single solution that pulls out the coherence and separates out all of the noise and outliers? And again, this fundamentally relies on the fact that there is low rank structure in my movie, okay? And so this is the optimization problem that was introduced by Candes and collaborators in image sciences to do this same thing, to clean up images. So what we want is we want our data matrix to be the sum of a low rank and a sparse matrix, where the rank of L is as small as possible, and the sparsity of S, it's as sparse as possible. It has as many zero entries as possible. Now, this is non-convex and cannot be solved in a tractable way, but you can relax to something that can be by swapping out the zero norm for a one norm and the rank for a nuclear norm. And so this can be solved using iterative optimization techniques on very large scale problems. And that's exactly what we use to make that movie in the top row. Okay, so that's actual data running this optimization. I'll point out, since I know a lot of us are really interested in turbulence and multi-scale systems with mixing, Isabel also applied this to the Johns Hopkins channel flow data that has this real scale separation. And she looks at trade-offs between, filtering small scale eddies and aggressiveness of the noise that you can filter. So I think there's some really interesting trade-offs there if you are interested in her paper. And so if you look at the true modes of the clean system on the left, you can approximate those with the bad X matrix, the salt and pepper noisy matrix in the middle column. And after we clean the data using our procedure, you almost perfectly recover the correct modes by decomposing L. Okay, so those low dimensional patterns come out. You can use those for modeling, like with the dynamic mode decomposition. So before cleaning the data, we get really poor models. All of the eigenvalues are supposed to be on that unit circle with the circles. After our filtering, most of our modes are on that unit circle corresponding to periodic structures. So we're doing a better job modeling here. Okay, and again, I'll point out this is the toy system that we tried it on, but we've applied this to experimental fluids, turbulent fluids, and you can really do this on multi-scale systems also. Good. So for the next example, where we're looking at fluids like image sequences, I'm going to talk about the super resolution problem. So this is another one that's very important to those of us who care about multi-scale aspects of these systems, climate modeling or LES closures, things like that. And so what we're going to do is use a shallow decoder architecture. This is work by Ben Erickson when he was postdoc working with Nathan Kutz and me. So we're going to use the shallow decoder to take a few measurements of our system and estimate the full high resolution image. And again, we're using Johns Hopkins data set here. So in the top row, what you see in panel B, that low resolution downsampled image is the input to our decoder, and the decoder is trained to fill in all of the high resolution structures. And I want to point out, this actually works really, really well for interpolation tasks. When my training data is large enough that I've seen everything that I'll ever see in the future, this works beautifully. And so if I take my time series of data and I train on all of the dark gray columns and I test on all of the light blue columns, I get nearly perfect image reconstruction from the super resolution task. But that's because these blue columns are essentially between two gray columns usually. In a more practical sense, usually what we want to do is we will collect data for some amount of time, and we'll want to use that training data to predict some estimate in the future. We'll want to use this model in the future. That's like in this lower right here. So maybe I train on 70% of those dark gray columns, and then I want to test on the next 30% of light blue columns. And what we find here is that we still get decent performance of reconstruction for short times after our training, but for longer times, it degrades very rapidly. And so this is a really important point. The more turbulent your system, the more kind of higher multi-scale structures you expect to see, the more training data you're going to need before you can really make this look like an interpolation problem. So neural networks in general are fantastic for interpolation, usually pretty bad for extrapolation. Okay, and so you need so much data that everything looks like an interpolation task. That's why ImageNet and Google Images and Facebook work so well, is because they have hundreds of millions, if not billions, of examples to train from. Okay, so this is kind of a caveat. Good. Okay, so for the second half of the talk, so lots of low-hanging fruit from image sciences. In the second half of the talk, I'm going to talk about how we use these kind of data-driven methods for getting reduced order models of fluid systems that we can then use, however we want, for control, for prediction, optimization, you name it. Okay, and I want to point out some just kind of philosophical points here. There are a lot of black box machine learning techniques out there, just big neural networks, and they're very powerful, very expressive. But I would try to motivate that we really have a need for interpretable and generalizable machine learning in the physical sciences, especially if we're going to use this on aircraft or automobiles where it's safety critical. And instead of giving you definitions, which no one agrees on what these definitions actually mean, I'm just going to show you what I mean. So by interpretable and generalizable, I think of Newton's second law, right? So Newton could learn F equals ma from an apple falling on Earth. And that law generalizes when we try to land humans on the moon. Okay, it's valid, completely different circumstances than apples falling on Earth. You could train a neural network on movies of apples falling all day long, and it would build a very good model of apples falling, but it would not get humans to the moon. Okay, so that's the generalizable piece. It is also interpretable in the sense that there are three terms, they have units, and we can discuss what they mean. Okay, so that's the kind of thing we want out of our machine learning, is more like F equals ma, less like a big neural network. And so, this idea of things being as simple or interpretable as possible goes way back. Thousands of years. Ptolemy was talking about this, Aristotle, all the way to now with, Newton and Einstein. And mathematically, the way we get these models is by using low-dimensional representations, so only a few variables, and getting sparse representations of the dynamics. Try to kill as many terms as possible so that F equals ma is as simple as possible. And those generally give us robust models that are interpretable and generalizable. So that's the perspective I'm going to be using in the remainder of this talk. Okay, is how we bring these ideas into machine learning. And so I want to talk a little bit about these mixing systems. So we're going to talk about chaotic thermal convection. And in the modern era, the kinds of models that we want that are interpretable, generalizable, are models like the Lorentz model. Okay, so very complex system. You can distill it down into a differential equation in three variables. It's low dimensional. And the right-hand sides are quite sparse. There's only a few terms that are active in that right-hand side. Out of all the possible dynamics, this is a relatively simple one. I'll point out that, I like to add Fetter and Hamilton now, because those were actually the graduate students that ran the supercomputer simulations for Lorentz to generate the data for this model. So I think by modern standards, they would almost certainly have been co-authors on those papers. And this is the same famous Hamilton from NASA, Margaret Hamilton. Okay, great. So this is the kind of model we want, are these simple Lorentz type models. Okay, so I'm going to walk you through one possible example of how to do this on this Lorentz system. So we assume that we collect data from the Lorentz system, x, y, and z. And for now, assume you can collect x dot, y dot, and z dot. So each row is a measurement at an instant in time. And the simplest thing we could do is just build a linear regression model. So we could build a linear regression model, the best fit 3x3 A matrix that maps x, y, and z to their derivatives. This is exactly what dynamic mode decomposition does. But DMD, I don't think any of us have confidence that a 3x3 linear model is going to capture the Lorentz system with multiple fixed points, chaos, unstable periodic orbits. This is almost a cartoon of why DMD sometimes fails, and it works really well for periodic systems, not so well for chaotic systems or truly nonlinear systems. So instead, what we're going to do is we're going to augment the right-hand side with more candidate functions that describe the dynamics. So instead of linear terms, we're going to include quadratic terms, x squared, xy, y squared, cubic, quintic, all the way up in this case to fifth order terms. And now the name of the game is to try to find the fewest columns of theta, the fewest of these possible terms that add up to equal x dot, that add up to equal y dot, and that add up to equal z dot. Now, 20 years ago, this would have been an intractably hard brute force search. This would not have scaled with Moore's law. But again, there are relaxations to this optimization problem that you can run that will give you with high probability the sparsest linear combination of theta that equals x dot, y dot, and z dot. So we call this the sparse identification of nonlinear dynamics, or SINDY for short. And what it gives you is the structure of your nonlinear dynamical system that best describes your measurement data. Okay, it's a pretty simple idea. If it only worked for this toy data, I probably wouldn't be showing it to you today. So what I really want to show you is how we have gotten this to work for much more complicated fluid modeling systems. Okay, but this is just kind of the cartoon of how it works on a system where we know the answer, because that's a great place to start. Okay. If you're interested in trying this out, we just released this on GitHub and in the Journal of Open Source Software, a Python version, so you can try this out yourself. And you can also use the same idea to uncover partial differential equations, either full PDEs or coarse-grained equations. So again, let's say I have my flow past a cylinder and I measure vorticity and my velocity fields, omega, u, and v in space and time. I can build that same linear algebra problem, but in the right-hand side, I can have partial derivatives of my variables and nonlinear products of partial derivatives. And so in this case, if I run sparse regression to find the best combination that equals my time derivative of vorticity, I come up with something that is structurally the same as the Navier-Stokes equation and has the Reynolds number to within about 1%. That's the pink terms highlighted there. Because there's so much data in these spatial temporal systems, you can also massively downsample your data and you still can recover these PDEs. Okay, so this is kind of useful. Collaborators have used this to find coarse-grained models of magnetohydrodynamic systems. And so we believe that there could in fact be a hierarchy of partial differential equations from full complexity to very low complexity and all of the models in between. At least that would be the goal. Okay, so let's go back to the fluid reduced order modeling and we'll look at our favorite low Reynolds number flow past a cylinder to start with. So Bernd Nowak and collaborators in 2003 showed us that there is a good coordinate system to model this, just like Lorentz knew there was a good coordinate system for Rayleigh-Benard convection. And in that coordinate system, the Navier-Stokes equations look quite simple. This blue boxed equation on the right, where there's this slow quadratic manifold, quadratic nonlinearities, and three variables that describe this transient and steady state behavior. So what we do is we collect that data, that time series data from the full simulation of x, y, z, and calculate the derivatives. And when we plug that into our SINDY algorithm, we uncover that structural dynamical system that Bernd Nowak derived from Galerkin projection. And our model has the same slow manifold, the same kind of transient behavior. And so what we call this Galerkin regression. So you're getting the same types of models you would get from Galerkin projection, but using this sparse regression procedure, okay? And very shortly after we wrote this paper, Jean-Christophe Loiseau from Paris Tech emailed me and made two really important improvements that I think are kind of the highlight of this work really now. One is that he showed that because what we're doing is the sparse regression to find the dynamics, you can enforce known constraints on the coefficients of your model, on what terms have to be equal and opposite and things like that to each other. So for fluid systems in compressible flows, we know how energy is conserved through these skew symmetric quadratic nonlinearities. We can enforce those symmetries by construction in our Cindy models so that every model we get has to conserve energy because it has the right skew symmetry. The other thing JC did was we tried to find quadratic models because Navier-Stokes is quadratic. Galerkin projection gives quadratic models. But JC gave us the possibility of including cubic, quintic, septic, nonic, higher order terms into the dynamics. And essentially what that does, if you look at this equation in the right, in the pink box, that Z dot equation, lambda is a very fast eigenvalue. And so very rapidly, Z equals x squared plus y squared. And if you substitute that in to the first two equations, you get the effect of a cubic term, even though you have quadratic nonlinearities. And the even faster terms that we're truncating in our Galerkin expansion, those would appear as fifth order terms and seventh order and ninth order. And so what JC has shown is that by including higher order terms, you can essentially get a rudimentary closure for all of the low energy but fast modes that we're truncating. Now, this is, of course, a laminar problem, so calling it a closure is a little overly ambitious, but it's still very suggestive of something that we might want to do in a more complex system. Okay, good. So let's see how it actually compares on two flow systems of interest, the cavity and the cylinder. So in the panel on the right, we see our state-of-the-art industry standard Galerkin projection onto POD modes. This is what everybody uses. The white curve is the figure of merit. It's a proxy for the drag in these cases, and that's what we're trying to measure or capture over time. The yellow and the blue are a 3-mode and a 7-mode, I believe it's 7-mode POD model. And you can see that they get the right qualitative behavior, but quantitatively, they're not perfect. Okay, they have overshoot, the steady state's not right, and the rise time is too fast. But when we apply these cubic and constrained Cindy models, we almost perfectly match the rise time, the steady state, and with almost no overshoot. Okay, and so we get more accurate models that are actually simpler than these 7 POD models. Ours only take 3 modes. And because our models are sparse and interpretable, you can actually write them down on pencil and paper. This is what JC did, and rearrange them. And what he wrote down is this essentially, this entire dynamics of the cylinder flow can be written down as a spring mass damper with a nonlinear damping, or a Van der Pol oscillator, if you like. To date, this is the most accurate and the simplest model of the cylinder flow in the literature that I'm aware of. And this is all facilitated by, again, giving ourselves the ability to constrain things to be energy conserving, adding in higher order terms to approximate low energy but fast modes, and applying sparsity so we get something that's interpretable, that we can actually manipulate. Okay. Good. You can apply this to more complicated systems like the fluidic pinball. This has 3 cylinders and you can get this kind of broadband behavior. And instead of measuring the full flow field and looking at flow field feature extraction, we can build these models just on lift and drag coefficient data from those 3 cylinders. So that's much more like what you would have in a real engineering application. Okay, good. So just in the last couple of minutes, I'll show you how we're applying this to these more complicated systems like thermal convection. And I'll highlight this great work by JC. This is work he did by himself recently, where he took this chaotic thermally driven thermosiphon. So it's basically a hula hoop that's hot on the bottom, cold on top, and it has the same chaotic oscillation behavior. And he was able to pull out essentially the data and run it through Cindy and show that he gets the exact same Lorentz dynamics as the regular Rayleigh-Bernard. So this is a totally different problem. He's able to show that it's structurally Lorentzian. Another example we've looked at is chaotic electroconvection, where you have a more complicated three-way coupling between your fluid, a charge density, and an electric field. Okay, a little bit more complicated. And in this case, what we were able to show is that from our flow field data, once we extract our POD modes, our low dimensional representation, the time history of the amplitudes of these modes in time show these incredible symmetries. So A1 corresponds to the amplitude of mode 1 in time, A2 is mode 2 in time, and so on. And there's just this incredible symmetry that comes out of this data because of properties of the physical system. And so you can actually uncover and write down what symmetries are in the data and then enforce those in our constrained Cindy models. And when you do that, you end up getting a sparse model that has the same structural dynamics, kind of the same skeleton as the full order system, and captures those same symmetries. And so just zooming in on the symmetries a little bit, we've listed the 5 symmetries on the right. And when you see those, that immediately kills a lot of terms in the model. There are terms that simply can't be there because they don't adhere to those symmetries. And so this also allows us to train more accurate models with less data because we're fitting less coefficients in our Cindy model. And so then going to the full system, we see that we're capturing the same kind of structural nonlinear dynamics where there are these different chaotic paths that are the system switching between in our low order system that is observed in the higher order system. Okay, the last example, because I see I'm out of time, is my excellent PhD student, Alan Kaptanoglu, has generalized this to even more complex systems in magnetohydrodynamics, where he has a spheromac fusion reactor. And again, extracting out these POD modes and time series so that you get an attractor, he can get these sparse, constrained structural models that almost perfectly match the observed dynamics. So really exciting that we can start applying these to actual systems where we don't know the answer, real multi-scale systems, and systems where we have partial knowledge of the physics. So we can, if we know how energy is conserved, we can start to bake this into our models. Okay, so with that, I should stop, and hopefully we have a few minutes for questions. Thank you all so much for your attention.